for the introduction. My name is Nicholas Bark from TU Dortmund University, and I want to introduce the Barkhausen model-based fatigue-large prediction on AISI 4140 ESD. First, I want to start with my motivation. Residual stresses are influencing the fatigue behavior. It's well known. Therefore, autofiltrage is a common process which is used in, for example, rails for a common rail system to induce compressive residual stresses in the surface layer of the part. This is a very time and cost-intensive procedure, and therefore we want to spare down this process by optimized drilling processes. We use a single-lip drilling process. Single-lip drilling is an asymmetrical drilling process where the passive forces are induced to the surface of the borehole, and therefore can induce compressive stresses. I want to validate the surface layer by the magnetic Barkhausen noise measurement. You can see here the schematic view of a magnetic sensor. We induce the magnetic field with the primary coil, the magnetic yoke in the material, and detect the magnetic answer by the induction coil and the magnetic field sensor. When we can see here the hysteresis of the magnetization. The H is the external magnetic field, and the B field is the answer of our material. When we go through the initial curve, we can see that the magnetic domains orientate according to the external magnetic field. This hysteresis is characterized by 2 points. On the one hand, the remanence point. It's the remaining magnetization in the material when there's no external magnetization. And the coercive field strength, which is the magnetic field we have to induce to have no internal magnetic field. This hysteresis is mainly influenced by lattice defects. We can see here the movement of the domain wall, which is inhibited by the lattice defect, in this case an exclusion. And it's also influenced by the magnetostriction, which means an orientation of the magnetic dipoles leads to a geometrical change of the material. And when this is inhibited, we can monitor the stretch conditions. This hysteresis isn't a steady process, but it's there are jumps. These are the so-called Barkhausen jumps. The magnetic hysteresis is changed by stresses, for example, the tensile stresses and compressive stresses. Change the coercive field strength, but the remanence stays the same. On the other hand, the hardness of the material change both. On the one hand, the coercive field strength, and on the other hand, the remanence. When we now apply a high-pass filter, we can see the Barkhausen loss jumps. We can see here the jumps over the external magnetic field, which is sinus 0 When we now put the Barkhausen noise jumps with the magnetic field, we came to this so-called butterfly curve, which with 3 different characteristic positions. The maximum of the Barkhausen noise jumps, which is correlated to the coercive field strength. The MRR is the Barkhausen noise highest in case of the remanence point, and the maximum Barkhausen noise. We can see here the maximum Barkhausen noise with 2 different materials, a hard and a soft material, with the residual stresses. We can see here that for one material we can clearly differentiate different stress states. But you can see, for example, at 1 volts, we can see either minus 300 megapascals or plus 300 megapascals, depending on the material. And therefore, we have also detected different magnetic properties. Here we can see the coercive field strength for the same material and can clearly differentiate between these 2 materials and the stress conditions. In this study, I looked at AISI 4140 with varying sulfur contents. It was like continuous casting. We can see here in the quench and tempered condition. It's just differentiated significantly in the sulfur content. The fatigue tests were performed on a homotestronic testing device with testing frequency of about 75 Hz, with an instrumentation by an extensometer, thermocouple, and the AISI potential probe. And moreover, I performed some magnetic Barkhausen noise measurements with these inner surface sensor. This is a custom-built sensor which can be placed inside the drilling hole of the specimen to measure the Barkhausen noise at the crucial inner surface. The surface conditions are mainly influenced by the drilling forces. As we can see, the feed force increases with increasing feed rate and is decreasing with higher sulfur content. This is also seen in the torque. And we can see here micrographs of the two different melts and the three different feed rates. And we can see that with increasing feed rate, the white layer is more pronounced. And even with higher sulfur content, the white etching layer is increasing. The scanning electron microscopes reveal that for the highest feed rate, the influence depth is the lowest. As you can see here, it's conventional instrumentation of a fatigue test. It has to be noticed that these tests were performed intermittent. Therefore, there's a drop every 10,000 cycles where we measure the Barkhausen noise because we can't do this in the fatigue test. You can see there is no clear differentiation, and the failure starts quite abrupt. This is also on the one hand of the plastic strain amplitude and also on the change in the temperature. Now we can see here the development of the quercetic field strength for lower sulfur content. We can see different things here. On the one hand, we can see for the feed rate 0.05 and 0.1, the initial state is comparable, and the initial state for 0.15 millimeters feed rate is lower. Therefore, we can differentiate the initial state. The micrographs before showed us that 0.05 and 0.1 have a comparable microstructure. And on the other hand, we can see after initial drop of 0.05, the following development is quite comparable for all three different feed rates. On the other hand, the coercitive field strength for the S280 melt also shows the differentiation between 0.05 and 0.1 and 0.15 millimeters, but afterwards there isn't a clear development. And even the scatter for 0.05 is very high. For the maximum magnetic Barkhausen noise measurement, the maximum of the magnetic Barkhausen noise amplitude for S110 even has a big scatter at the beginning and doesn't develop afterwards. On the other hand, for the higher sulfur content, we have after initial drop a very clear comparison of the magnetic parameters. Therefore, afterwards I normalized the coercitive field strength for the S110 on the second point. It's important for the second point to don't look at the initial drop. I normalized it, and you can see we have development for two different stress amplitudes and for all three different feed rates, which can be described with this quadratic excitation. For the S280, we can't use the coercitive field strength, we have to use the maximum Barkhausen noise amplitude. And we can see here we have normalized on the first point because we had a big drop at the initial state. And we can describe the development of the Barkhausen, of the maximum Barkhausen noise with these describe the fatigue behavior for with the Barkhausen noise measurement. What can we say in conclusion? We can differentiate the initial state, which is mainly influenced by the material, well, therefore the melt, and the production properties, in this case the feed rate. We have a significant change in the first 10,000 cycles, and we are capable to detect the material degradation over the fatigue test and estimate. We can estimate the fatigue damage after above approximately 20% of the fatigue life. And in future, we should do a more detailed investigation on the micromagnetic parameters, on the influences on the micromagnetic parameters. If it's caused by residual stresses, work hardening of the microstructure, and therefore can come to an advanced correlation of the fatigue damage and the micromagnetic parameters. I want to show you some references and an acknowledgement to the Deutsche Forschungsgemeinschaft, and thank you for your attention.